Good evening, everyone. I think not many people have joined today, but as I have to record it for a session so that you can see it afterwards, so this may help you in solving assignments. So, today I am going to present 10 questions on the basis of week 5 classes, which was generally based on solar cells, and I will be happy to address if you will be having any doubt afterwards. So we can start by 6:10 p.m. But before we start, I just wanted to tell you, I hope you have already gone by this website, but if not, then I just wanted to show you that there is this website PV Education on which you can go, and this website actually has all the details, all the basics of what we are actually studying in this course. So if you go to the semiconductor and junction, you can see that there are basics of semiconductors, its structure, the band gap, intrinsic, how do we do doping, and this generation, types of recombination, diffusion and drift current, and how does a depletion region forms, a p-n junction, and the equations and solutions of some question on the basis of depletion regions. Anyways, so in today's class we will be having questions on the basis of solar cell operations. So if you go to the solar cell operations, we can see on this website, basically to start with a solar cell structure, and then there is many stuff. If you can see here in this website, that light generated current, collection probability, quantum efficiency, spectral response, photovoltaic effect. These are the basics of ideal solar cell, and after that there are certain solar cell parameters, which is IV curve, short circuit current, open circuit voltage, fill factor, efficiency, detail balance, tandem cells, and etc. And then there are certain characteristics, and then there are certain effects, that what is the effect of temperature and light intensity and the ideality factor with respect to the solar cells. Okay, great. So let's wait for some time, so that others may join in the meantime, and then we can start. Okay, so yeah, if not anyone will join in this today's class, because it is not as per the scheduled day. I'm keeping it on Sunday, except as in Saturday. So I'll not be waiting for the answers. I will just be showing the questions, and I'll be discussing the answers and showing you the solution. That's it. So I'm waiting for 4 more minutes if somebody joins. If not, then it's okay. Let me give a check also if it is recording properly. Yes, it is. So I'm just waiting for 4 to 5 more minutes, and then I'll start answering on my own, discussing on my own. I'll first discuss certain basics of the solar cell, and then I'll discuss 10 questions based on it, and then I'll share the slides and the PDF, and the video also on the YouTube channel. You all can see afterwards. Okay, so I guess not many people will join today, so I'm going to start. So I'm just starting with the basics. Okay, so if I talk about the solar cell structure, so basically a solar cell is an electronic device which directly converts sunlight into electricity. Okay, so as we can see, the light is shining here. This is a electron and hole pair which is generating. Okay, now this process requires firstly a material in which the absorption of the light raises an electron to a higher energy state, and then the movement of this higher energy electron from the solar cell into an external circuit. The electron then dissipates its energy in the external circuit and returns to the solar cell. A variety of materials and processes can potentially satisfy the requirements for photovoltaic energy conversion, but in practice, nearly all photovoltaic energy conversion uses semiconductor materials in the form of a p-n junction. Okay, so the basic steps in the operation of the solar cell are the generation of the light generated carriers, and then the collection of light generated carries to generate a current, the generation of a large voltage across the solar cell, and the dissipation of power in the load and parasitic resistances. Okay, so they are the four basic steps. In if you talk about the general cross section solar cell, that's very basic. I'm not going for a specific type, that dye sensitized or perovskite. I'm normally telling you just a cross section picture of a general solar cell, a modern solar cell. Now there are many terms that you need to figure out. This is light generated current. How does this light generated current takes place? You can see when the light falls down here, absorption of a photon creates an electron hole pair, and then this electron is moving to the load. Ideally the minority carrier in this case is a hole which makes it across a junction. This is the junction, becomes a majority carrier, and then this is going to the rear contact, on which passing through the load the electron meets up with a hole and completes the circuit. This generates the light generated current. Okay, now that there is another term called collection probability. You can see it describes the probability that a carrier generated by light absorption in a certain region of the device will be collected by the p-n junction, and it therefore contribute to the light generated current. This is the collection probability. If a unity collection probability for carriers generated in the p-n junction. Okay. Okay, then comes some other factors. The quantum efficiency is there. If you talk about the quantum efficiency, it is the ratio in the number of carriers collected by the solar cell to the number of photons of a given energy incident on the solar cell. The quantum efficiency may be given either as a function of wavelength or of energy. If all photons of a certain wavelength are absorbed and the resulting minority carriers are collected, then the quantum efficiency at that particular wavelength is unity. Okay, if you see this, blue response is reduced due to the front surface recombination. The red response is reduced due to the rear surface recombination, reduced absorption at the long wavelengths, and low diffusion lengths. This is the ideal quantum efficiency curve. Here no light is absorbed. You can see this is of a silicon solar cell. Then there is this spectral response. You can see, you can go through it. Then the concept of photovoltaic effect. How does it tells that this electronic diffusion and electron drift takes place when there is no light, and then this light generates extra carriers, and then there is a small field across the external circuit, then and the short circuit current. Okay, when a complete circuit is there, this is how it takes place. Now the certain basic terms that we have to go today is, I will be telling you I have certain numericals today, therefore I want to go start with the basics of these solar cell parameters only. So I will be telling you about IV curve, short circuit current, open circuit voltage, and fill factor and efficiency, so that the numericals that I will be solving afterward, it may be, mm, properly understood. So if I start with the IV curve, you can see, this is the The IV curve of a solar cell is the superposition of the IV curve of solar cell diode in the dark with the light generated current. The light has the effect of shifting the IV curve down to the fourth quadrant where power can be extracted from the diode, illuminating a cell as to the normal dark current in the diode so that the diode law becomes. Hello Mele. So actually nobody was there, so I was actually recording the class for seeing it later. So just to show you, I have 10 questions today on the basis of week 5 classes, which are generally based on solar cells. So before
That's all, sir. Good evening, sir.
good evening, good evening. Am I audible, right?
Yes, sir.
Yeah. So I was discussing the solar cell, like if you open this website PB Education.
Yes, sir. PB education.
Yeah, there if you go to the solar cell operations, okay, then these two things you have to go through if before the like after going through the classes of the sir, where you can really see the solar cell structure, the basic structure, and then how this light generated current takes place, the collection probability and the quantum efficiency, and then the photovoltaic effect. Okay, I have already taught before, like already recorded it before you joined. So you can see it afterwards. right now
Okay.
right now I'm just discussing these things: IV curve, short circuit current, open circuit voltage, fill factor and efficiency. Why I'm discussing all of it? I'm discussing all of it because today's questions are based on these, and these are the basic solar cell parameters. Okay, so if I talk about the IV curve, Melee, so IB curve is the current versus voltage curve. If we talk about the IB curve of a solar cell, no, so it is a superposition of the IV curve of the solar cell diode in the dark with the light generated current. The equation is I equal to I naught exponential QB over NKT minus 1 minus IL. Okay, where IL is a light generated current. If I want to show you the video, then without illumination a solar cell has the same electrical characteristic as a large diode. You can see the IV curve. Okay, now when the light is shining on the cell, the IV curve shifts as the cell begins to generate power, as you can see here, Mele. Okay, it is getting shifted, and this is because of the shining of the light on this diode. Now the greater the light intensity, the greater the amount of shift. Okay, the greater will be the light intensity, the greater will be the amount of shift, and the solar cell curve is flipped by convention. Generally this is this one. When we show it in the solar cell, we show the flipped version of it. Okay, so we can say the ideal short circuit flow of electron and holes at a p-n junction, minority carriers cannot cross a cross semiconductor metal boundary, and to prevent recombination they must be collected by the junction if they are to contribute the flow. So basically this is a convention. When the light is falling, there is generation of light current, IL and I diode. Now when you're increasing the intensity, this is you are having a great amount of shift in IV curve, and generally in the convention for solar cell we show this is about the IV curve. Now what is short circuit current and what is open circuit voltage, fill factor and efficiency? The most important term, if you are learning solar cell you should know it. So let's start with the short circuit current. Today's many questions are based on this short circuit current and open circuit voltage. Okay, so if I talk about the short circuit current, Melee, the short circuit current is a current through the solar cell. Yeah, so if I talk about the short circuit current is a current through the solar cell when the voltage across the solar cell is zero. That is, when the solar cell is not short circuited. Usually we write it as ISC. The short circuit current is shown in this IV curve. Okay, so this is a short circuit current where when there is no when there is no voltage. Okay, that means zero voltage. The short circuit current is the maximum current from a solar cell that occurs when the voltage is zero. Okay, and if I talk about the open circuit voltage, which is represented as BOC, this is the maximum voltage from a solar cell. It occurs when the current is zero. Remember it, short circuit current is the maximum amount of current when the voltage is zero, and open circuit voltage is the maximum amount of voltage in the solar cell which occurs when the net current through the device is zero. After this comes the concept of fill factor and efficiency. what is fill factor. I have certain numericals related to this also. Now, when you know the concept of short circuit current and open circuit voltage, the short circuit current and the open circuit voltage are the maximum current and voltage respectively from a solar cell. That is the current and voltage which you should have in an ideal condition. But when you are considering the operating points, the power from the solar cell is still zero. So the fill factor, more commonly known by the abbreviation FF, is a parameter which in junction with VOC and ISC determines the maximum power of a solar cell. The fill factor is defined as a ratio of maximum power from the solar cell to the product of VOC and ISC. Remember it, Malley and Shruti, fill factor equal to PMP over VOC cross ISC. You can see here, this is ISC, this is VOC, this is the area for a smaller area A is smaller for lower FF, and area this is higher for higher FF. That BMP means maximum power output voltage and maximum power output current. So this is fill factor. Ideally, the higher the fill factor, higher is good is the solar cell. And then comes the concept of efficiency, which is generally represented as eta. So the formula of efficiency is equal to open circuit voltage cross short circuit current cross fill factor over PIN. Okay, so you can see these are the terms, and now we can start today. So what I have talked till now, I have actually talked till now is what is the general convention of a solar cell, how these light generation carriers takes place, how these photons flow through the circuit, and when there is this general structure of a solar cell, what are the basic terms that we should know. Sir has already taught. The basic terms that should be kept in mind is short circuit voltage, current, open circuit voltage, the IV curve, the quantum efficiency, and some other basic things. You should know it, and along with the photovoltaic effect. So I think sir has already taught it, and if you have not understood, you can go by these slides, and if not, then you can go by this website that I have already shown. So I think,
Sir,
yeah.
sir, what is actually in assignment number 5, sir?
Hmm.
Question number 4 and 5.
Hmm.
I think the answer is wrong.
My assignment 5.
No, no, no. In week 5 assignment.
Oh, that you send me by mail. Okay, you send me my mail. I'll see and have a look. I have not looked through it. That is being uploaded by
Okay.
sir only. Okay, I have not checked it. You upload. You send me a mail. You know my email ID, right?
Yes. Sir.
So you send me a mail. I'll look with, and if this is wrong, then I'll inform sir. Definitely, you send me an
Oh,
email. Okay.
okay, sir.
Okay. So
And
today,
sir, what is the question pattern at final exam, sir? You told me today you discuss
yeah, it is same. The tick mark questions will come.
only objectives.
Yeah.
Okay, sir.
Okay. So if I show you today, let's start today's like we will not be having a lot of discussion because Melee, as you are alone, and those who will be watching the video afterward, they should not take it very boring. So yeah, because people watch it the recording, they don't attend it regularly. I have seen the views are there on the YouTube videos. So let's start today. So as I have already talked about the power conversion efficiency and all this saturation current and fill factor and all this, so I have these kind of questions today, 10 questions. So I will be discussing all these 10 questions. So let's go to the first question. The first question is saying, consider a PN junction. Just a minute. Consider a PN junction diode of area 1 centimeter square, which is under illumination of 100 milliwatt per centimeter square, that gives a short circuit current density of 25 milliampere per centimeter square and open circuit voltage of 1 volt, and generates maximum power of 20 milliwatt. The power conversion efficiency in percentage of the diode will be. The options are 15.5, 17.2, 18.1, 19.5 and 20.0. So you can give a try, Melee, if you want. I can give you 2-3 minutes. It's a direct formula based question, so you can give a try, and if not, then I'll tell you the solution. Mele, you can solve it.
No, sir. I am thanks. No.
Yeah, okay, try.
Calculate the field factor first.
Hmm.
Sir, the answer E.
Okay, let's see. So I have this solution. This is just question with, and I in every PDF I'm sharing this drive backup and website for best use.
Okay, sir.
So let's,
Answer E.
okay. So the question was asking about the power conversion efficiency. The power conversion efficiency was open circuit.
First, I calculate field factor, then multiply by ISC POC by power PS in area into illumination.
Good, very good, very good.
It's dominant.
Exactly. So let's see. If you see, that means 1 cross 25 fill factor will be 80, and p in, as you said, we have calculated by multiplying them, so the answer will be E, 20%. I don't think there is anything to explain into it, right, Mele?
Yes, sir.
Yeah, it's a
No,
form.
no problem. But sir, here there is a two step, na sir. By calculating the field factor, you directly write 80 as a field factor.
Yeah, you need to calculate the fill factor.
You reversed one step. That's right.
Yeah,
Miss.
I skipped one step because something to you have to do, no?
Okay, okay.
Okay.
Then already I have first calculate the field factor.
Yes.
Then without this,
Okay. Okay. Now let's move to the second question. The second question is also very easy, Mele. The second question is saying consider a P plus N silicon diode with acceptor and donor ion concentration as 10 is to 17 centimeter cube inverse and 10 is to 16
as I
centimeter.
want the formula, sir, I left it in assignment.
Okay, just a minute.
This
So,
question I left in assignment.
okay, so
11.
I'll show you the solution. So
Yes, sir, right.
the whole diffusion coefficients in the n side is 10 centimeter square per second, and tau p is equals to 10 is to power minus 7 seconds. So when the activity area of the device is 10 is to the power minus 4 centimeter square, the reverse saturation current in the diode will be when they have given the Ni, Boltzmann constant, and electron change. The options are like this. Okay, Mele, even if you have forgot the formula, I mean I have given you a sheet in my PDFs at last which is having all the formula in concise form. Even if you have forgotten it, I have already told you how to approach a question. Now let me again tell you. See, they are asking about the reverse saturation current. Even if you are confused that you don't know what is reverse saturation current, you know that they have given this concentrations of ion of acceptor and donor as 10 is to the power 17 and 16, and they have given the whole diffusion coefficient as 10 centimeter square per second, and lifetime on the p side as 10 is to the minus 7 second, and the area, and they have given the concentrations also. So one thing is sure, that first of all we need to figure out that what is the basic things that we need for finding out the saturation current in ampere. Do we have it? If we don't have it, what we have and what do we need to calculate? First of all we calculate that and then we approach the question. Okay, without delaying further, because we were not able to solve it, let me show you the solution. See, the solution is like this. If I show you the solution, Mele, the reverse saturation current formula is qa dppn over lp. Okay, now from the very first and second class, if you remember, we how did we calculate this concentration on the p side? Pn equal to ni square over nd. Are you remembering it, Mele? Are you following it?
Yes, sir.
Okay,
Yes, sir. I know.
now this ni is given as 10 is to 10 already to us. If you can see here, intrinsic carrier concentration. So ni square over nd, if we put nd means this donor ion concentration, then we can get the concentration on the p side, right? Hello.
Okay, sir.
Yeah, so from here
Yes, sir.
we calculated the pn. Now we had the value of tau p. From there we calculate the value of lp. Lp equal to under root of dp tau p, that means 10 cross 10 is to power minus 7, that is 10 is to power minus 3 centimeter. Now we know the formula of reverse saturation current, which is qa dp pn over lp. That means q is 1.6 into 10 to the minus 19 coulomb, cross a cross dp cross pn, that is 10 is to minus 4 cross 10 cross 10 is to power 4, what we have calculated. And then from here lp, we put it the value of lp in the formula, all these things are cutted out, then we calculated. The answer is 1.6 into 10 is to power minus 15 ampere. That means the correct option is option B. So you
Okay,
can have a look over it once more. If you want to write, you can write also, Mele.
okay, already I have written, sir, in copy.
Okay, great. Just remember this formula. I have told you that you have to figure it out, that what are the terms that you need to know. Now again, how to approach this question, Mele, just one more time. You had this p present side and donor ion concentration was given to you. Okay, that was 10 is to power 16. That means nd was given to you and intrinsic R
Yes.
concentration was given to you. From here you calculated pn. Okay, now from pn, how this dp and tau p is given to you, that must have been given to you for a reason, right? That
Yes,
means
yes, this
from
is
here
correct.
you calculated lp and then this is the formula.
No.
Now if you will now one more trick, if you will cancel the unit of this, no, then the unit you will be getting in ampere. Another approach is Mele. Suppose you are given something and you are not able to find out the formula, or you have forgotten, or there is something which you have not attended by chance. You try to make the formula yourself by using a logic, and see the answer that you want. The unit after cancelling the unit, the formula that you have put it. Are you getting the same unit or not? Then you put the value. Are you getting me?
Okay, sir. Okay.
Yeah, this, like when I was doing this numerical solving, let me tell you, I went for an entrance exam, and then there is this numerical aptitude type of questions. Okay, out of these 10 questions, you don't believe, Mele, I only knew 5. Okay, but because I had this approach of solving questions, what I used to do, I knew the concept, but I'm not remembering the exact formula, or I have not read that exact thing. So I used to figure out that what are in this question that I know. Okay, now what are they asking, and if they are asking this, what could be the possible thing that is required to find out. Now if there is a certain term that I don't know, then I try to make the formula. So how I try to make the formula, I used to with the logic, I used to put the unit accordingly, like put the parameters in the unit, and then I used to cancel out the units and see that the thing that is being asked in the question, am I getting the same unit with the formula that I have put it. And you won't believe, Mele,
Okay.
out of 10 question I solved 9 question and 9 were right. so
Yes, sir.
so 5 I were knowing, but 4 I solved like
No.
this, because I had to approach
By
with a logic. Okay, so you
Yes.
can follow this approach in the numericals especially. I really like to
Okay.
solve numerical, because there, even if you don't know and you are having some logic, you can solve it. This is what my feeling in physical chemistry actually. Okay,
Okay.
yeah, so anyways, let's move to the next question. So this is clear, I guess, and these kind of questions will be there, Mele. Okay, I think this question
Okay, sir.
in the assignment, now you know it. The question number 3 is, consider a PN junction diode of area 1 centimeter square under illumination of 100 milliwatt per centimeter square, which gives a short circuit current density of 25 milliampere per centimeter square, and open circuit voltage of 1 volt, and generates maximum power of 20 milliwatt. The fill factor in percentage of the diode will be. They are asking a fill factor. It's a 1 minute question for you, Mele.
80.
Great. Anyways, so as I am recording, others will be seeing afterward. Let me show the solution to them. So they are asking the fill factor. So if we have to calculate the fill factor, we have to approach this by this equation. Fill factor means P over VOC cross JSC. P max was given, VOC cross JSC, that is 0.8. Now we have to convert it into percentage, that means multiply it by
Yes.
100. That means fill factor in percentage will be 80%. Okay, great, good, Mele. So now let's move to the next question. The question number 4 is saying there is a single solar cell 10 centimeter cross 10 centimeter which produces a voltage of 0.5 volt and a current up to 2.5 ampere. If the solar insolation is 800 watt per meter square, the efficiency of the solar cell is. Now you follow the approach I told to you, Mele. Let me see if you can solve this question. You have given the area of the solar cell, you have given the voltage and the current. Now there is something solar
Yes.
insolation, and you have to calculate the efficiency. You know the formula of efficiency already. Now,
Yes, sir.
now you see what is there, and then also find out that the answer that you are getting, are you getting somewhere like the options that you are given. That also is a trick. Okay, try to do it. If not, I'll show you. Not a big deal.
I think question number two. I think.
Question number 2 means,
Sorry, answer number two.
okay, 24.6% you are saying.
No, I think.
Okay, so as nobody else is there,
No,
I'll,
I'll calculate, sir. Then.
yeah, give a check if your answer is right. Okay, so let's see. So given values is solar insolation is 800 watt per meter square, voltage is 0.5 volt, and current is 2.5 ampere. Efficiency we need to calculate, Mele, and the area is
Yes.
given 10 centimeter cross 10 centimeter. That means 10 is to the power minus 2 meter square. Okay, we have to convert it into meter square. Because why? Because
Okay.
this solar insolation unit is given in meter square. Okay,
In meter.
yeah.
Yes.
Now let's see. Efficiency is this, solar insulation is given, power output voltage is voltage into current. Now I don't know, I think uh, something is missing there. uh, Anyways, so if you will put the value of V and I for the power output voltage, and then I think this is incomplete. I have put it in the PDF.
Sir, 1 minute. What is the power?
Uh,
Current
the
2.5, voltage 0.5.
2.5 voltage 0.5, yeah, yeah, that will be the power, and solar insulation is given, and efficiency will be that the formula same. So from there we can calculate the efficiency formula was what, if you remember from.
Then VOC ISC into fill factor by power out,
Hmm.
incident power.
Hmm. So from there, what is the answer that is coming, Mele?
Sir, I am calculating, sir. Incident power.
Hmm.
Sir, can you see me the question once?
Okay.
Okay, sir. Sir, during fill factor calculation, sir,
Hmm.
sir, what is the maximum power drawn from the by the solar cell? How can I can calculate? Because option is not given, na, sir.
Yeah, exactly. That's what I am thinking. I think I have given some less information in this question. I am finding out. Okay,
Yes, sir. That's why.
Mele,
Yes, sir.
I will put the solution of this question right in the PDF. You download the PDF later, okay? Because right
Okay.
now the time is going. But the answer is 15.6%. Okay, because
Okay.
I
Okay.
don't know. I have made this PDF, but I am not able to see the equations. This has become blank here.
Yes.
You can see here.
Okay,
So
sir. You update it, sir.
I will upload it, okay? And if you have then
Okay,
doubt,
sir.
then you can ask it later. Because I'm myself getting confused in the question that have I given the right value? Something is missing.
Sir, everything is there because in field factor we want suppose question number three we
Hmm.
have the generate maximum power. We
Hmm.
want it. Otherwise we cannot find field factor.
Hmm. Hmm. Exactly, that's what I'm saying. Because power maximum is not given.
Given, yes, sir.
Except that the voltage and the current was given, and the area we have already calculated, right?
Area already calculated.
Yeah, but what they have given this, if you can see, solar insolation. So if this solar insolation you can use as a power, this is watt per meter square, and you have the area point 0.1. So that means for point 0.1 meter square the solar insolation will be 80 watt. So if you use this 80
Yes.
watt, then what is the answer that is coming? Could you check?
80 watt. Okay,
Yeah.
okay. Then I have to do it. Sir, fill factor is coming 64.
Okay. So the if you put it the equation, then the form answer will be this formula you can use VUC ISC over power incident.
Coming 100, sir.
Yeah, actually mine is also coming 100. So
100.
yeah, I'll tell you the solution of this. I think some value is there which is misinterpreted, I guess.
Yes, sir. It's coming 100.
Yeah. So I'll update the solution of it, but the right answer is 15.62%. Okay. So I'll update
Oh,
the solution in the later one. So without dealing further, in the PDF I'll update it because this question was made by me, so I put it some wrong value, I guess. Okay. I
okay.
have taken it from some website, I guess. Okay, let's move to the next question. These two, three questions are these basic questions on the basis of concept. So, question number 5 is saying is following are the correct for the design and operation of an efficient photovoltaic device, where Eg is the band gap of the semiconductor. Low mobility of charge carriers should be there, or minimization of recombination rate throughout the device, or there should be high surface reflection from the cell surface, maximization of the absorption of photons with E greater than the band gap, low surface reflection from the cell surface. So among these, which are the correct?
Sir, E and D. E
E,
and D,
D and E.
100% sure.
Yeah,
And
D.
B also. B.
Great. Why do you think the low mobility of charge carrier is not right, Mele?
The charge carrier's mobility should be high.
Yeah, exactly. Then if
Otherwise, current will not.
not flow, the higher the charge carrier mobility, the higher will be the magnitude of the current. Great. Now let's discuss the B. Minimization of recombination rates throughout the device. Why it should be
Yes.
minimized?
Sir, if minimize recombination, will charge carrier will end. Electron will recombine. We need to carry the all the charge carriers, sir,
Exactly.
for
Flowing
mobility.
for flowing in the circuit, right?
Going to N to P.
Yeah. Okay, great. Now high surface reflection from the solar cell. If there will be more surface reflection, then what could be the drawback?
Sir, surface reflection, if making done, then we are the photo. Actually, we cannot get the photons, sir. They will deflect. That's why
Exactly.
we do texturing.
Yeah. That
Texturing.
where.
One plane we are doing
Yeah.
before the top layer.
Exactly. Very good. Very good. And there comes the
In first generation, sir, explaining first
Yeah.
generation lecture.
Hmm. 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 Yeah, exactly, and there comes the concept of absorption coefficient also. If it will be
Yes,
highly reflective, then it will not be able to absorb, right? Then there will be less generation of
absolutely.
the photons. Okay, then fourth and fifth are very obvious. The maximization of the absorption of photons with energy greater than the band gap. If this
Which
will be,
must be greater than EG.
yeah, then only this electron can jump, right? And then there will
Jump.
be
Yes.
low surface reflection. This is same, like this is the opposite of C, low surface reflection from the cell surface. This means B, D and E. So the correct answers are uh, B, D and
Okay.
E.
B, D, and
E. Okay.
E. Okay. Okay, sir. Same.
Yeah. Now let's move to the next question. The next question is the improvement in the fill factor of a particular solar cell device would necessarily lead to. Options are increase in open circuit voltage, decrease in the bias dependent current, increase in the short circuit current, or increase in the maximum power extracted.
Sir, D. First D. Increase the maximum power extracted.
Okay, and what about A, B, and C?
C. First C. Increase the short circuit current.
Okay, if you increase the short circuit current, then how will it lead to the increasement in the fill factor?
Sir, it's short circuit current. 1 minute, sir. It will decrease. No, sir. It will inversely proportion.
Hmm. If you see the
with VOC and ISC
yeah, if you
fill
see
factor.
if you see the
Yes,
form
sir. Inversely proportional.
if you see the formula of fill factor directly, then this
Yes.
question is directly
It's
dependent on this theoretical.
inversely proportional, sir. Yes, sir.
Yeah, P max
VOC by
over.
ISC by P max.
Yeah, so that means lower the short circuit current, lower the open circuit voltage, higher is the fill factor, and if higher is the
Okay.
maximum power output, then higher is the fill factor. Okay.
Fill factor.
Yeah.
Okay, sir. Can you show me the options again?
Okay.
A is wrong.
Hmm.
A is wrong. Decrease the vertical current. B is right.
Okay.
Increase the short circuit current. Wrong.
Hmm.
Then B and D.
Okay. Great. It was an easy question. So let's see. The answers are B and D. Right. Great. Easy question, right, Mele?
Yes, sir. Yes.
Okay. Let's move to the next question. For a PN junction photovoltaic device, as temperature increases, then what is the effect of
A,
temperature? Mainly.
VOC decrease
Hmm.
and JSC increase.
Okay. How do you know it?
Sir, actually by graph, sir.
Great. So if I show you the graph again, this is the graph. Okay. So how
Yes.
do you know
Sir,
will
no,
it?
sir. This is not the graph, sir. The
Okay.
temperature change, sir.
Great.
There is a graph temperature change. Different change of temperature. ISC increases
I'm
as
showing
well
you.
as
I'm showing
VOC
you. I'm showing you.
decreases.
I'm showing you. This is there.
This one.
Yeah. So the equation that is relating is this. If you want to go through it, it is a very lengthy equation. Okay.
Yes, sir. Yes.
So if you have a look over this equation, so the impact of I naught on the circuit can be calculated by these equations, and the general theory that you have to see, when there is a high temperature, this ISC increases slightly and the VOC decreases. So this is the effect of temperature on the short circuit current and the open circuit voltage. So the correct options are mainly VOC decreases in a PN junction device,
Yes.
mainly because
Yes.
you can see this ISC increase is very
Very
slight,
slight.
and it generally
The
does not.
option is not given, sir. Option also not given.
Yeah,
ISC increases.
and this mainly VOC there is a decrease, and accordingly the fill factor will be also managed. Okay, Male.
Yes.
If
Yes,
I
sir.
if I frame a question in this term, that what is the impact on fill factor, then you can tell, right?
Yes, sir.
Okay.
We need to formula inversely proportional both are.
Yeah. Okay. Who has joined, by the way? Mayank. Hello, Mayank. Mayank, am I audible?
Sir, this is the reason why we are putting solar plant in Ladakh.
Yeah.
No, not sir, not only solar plant, we are putting solar cookers, concentrating solar heaters
Yeah, you can say that, but
in Ladakh.
these are not the only factors. Like, let me tell you something, Mele. You are you're talking on the basis of these ideal equations. These equations are very ideal. Now when you are doing the fabrication in real sense, like, yes, first of all you know the concept. Now suppose you are making a perovskite solar cell, when which will
Yes.
be taught to you later. Now for making these perovskite solar cells, you need a whole transport layer, you need an electron transport layer, and then there are many types of the architecture. The architecture can be NIP, like first N, then I, then P. It could be PIN. That means inverted and non-inverted. Now what happens when you fabricate it? You generally use a FTO. Okay, on this FTO you put the electron transport layer, and then you put the perovskite material, then you put the whole transport layer, then you put the gold coating and all this parameter you set. Now you have to do all these things in globe box. You know what is globe box, Mele?
Yes, sir.
Globe box.
No, sir.
Okay, globe box is like it's a totally like inert environment. You have a big gloves are there. If you remember my very first class, I was showing you, I was taking the class in a lab where there was a glow box placed behind me. I can show you if you want. Just a minute.
Yes, sir. Yes, sir. I remember. Globe box was there
Yeah.
behind you.
Yeah, this is a glow box. So we generally do the fabrication inside it. Now what happens ki we are making the solar cell at the ideal conditions, but when we are putting it in the ambient conditions, there are many factors. All these equations that we are talking about are generally followed in these ideal conditions, Mele. But when we are putting in the real condition, then there is atmospheric pressure, there is humidity, there could be different variations, there could be some other ion migration, many factors are there. So yeah, you can say that yes, there is a proper reason if you consider ideally, but this is not the only reason. Realistically, when you are thinking, then you have to consider all these parameters in order to design a solar cell. Are you getting me?
Yes, sir.
Okay. So yeah, but yes, your approach is right. If you terms ideally, then your reasons are right. Okay, Mayank has already left. He joined and he left, I guess. Okay. So let's move to next question. A solar cell has an open circuit voltage of 0.62 volt for sun intensity of 2. Assume V tau is equals to 26 millivolt. For open circuit voltage of 0.58 volt, the value of sun intensity is X. Then X is what? See, they have given the sun intensity value for a open circuit voltage of 0.62. Now they have asked the sun intensity value for an open circuit voltage of 0.58 volt. That's the question.
So 1 minute. So what is the formula?
Okay, let me show it to you. So if I tell this question was, I think, not that much mentioned. This is the formula. So a
Sorry,
PN
Baba.
junction, if I talk about a solar cell, a PN junction diode with a wider depletion width used for the conversion of photo to the electric signal. Okay. Now the current and the voltage relation for a solar cell is given by VOC equal to VT ln ISC over I naught. If you can see, are you able to see? So
Yes, sir. Sir, what is VT?
VT is like, you can say, ideally the total voltage, the
Sir,
actual,
which voltage?
the total.
Okay.
Okay, so if you see ISC equal to I naught EVOC over NBT, this equation I have already shown you. So for
Yes.
sun intensity of unit X, you can see VOC equal to VT ln IOC X over I naught. Now putting these value in the equation, you got VOC1 equal to 0.62 volt, X1 equal to 2. So VOC2 equal to 0.5 volt, X2 equal to 7. For VT equal to 26 millivolt. Are you getting me?
Yes, sir.
So if you calculate the VOC1 from here, the VOC2 will be what? 0.58, and X2 is what? So from here, if you put the value of VOC1, that is 0.58 VT ln X2 IST over I naught, subtract, and this is the equation 1. Like, Malay, for these two cases
Yes.
you have put it these two equations for these equation. Okay, now you are subtracting the equation 2 from equation 1, which is giving you this formula. So the value of x2 will be 2 over this. That means,
Exponential.
yeah,
Yes.
x2 is 0.433.
Yes,
This
yes.
question will not be there, but I just put it for a brainstorming. Okay.
Okay, sir.
Okay, now I have two more questions. The first, ninth question is, what is a solar array? Could you tell me what is a solar array? Mele, I just put it
Yes,
for
sir.
increasing your knowledge. What is a solar array? Is it a cascade of a connected solar plant, or a combination of a solar panel with inverter, series and parallel combination of solar cells, or parallel combination of solar plant with another plant?
The cascade connects set of plant.
Okay, so you are saying that more than one solar plants
I
are.
think as sir, solar array is connection of multiple solar modules.
Yeah, exactly. Array is what?
Yes, I know it.
If you consider what is an array, like array is
Uh,
just collection of. And if you're talking
Correct.
in terms of solar array, let me show you. What is a solar array? Solar array is combining several solar cells in series of a parallel creates an array. Okay. So if you combine many solar cell in series of a parallel, it creates an array. So the size of
Sir,
a,
what is the series of parallel?
like you connect more than one in parallel combinations.
Okay.
Okay.
So this one connected in series.
Yeah. So the size of your solar array depends on the position of the roof and the energy requirement. A solar array can be used for solar heating, electric power generation, and lighting of spaces. For maximum current rating, the solar array is grouped in parallel. You remember it. If you need more
Yes,
current, then the solar array should be grouped in parallel. For maximum voltage rating, the solar array should be grouped in series.
grouped in series.
So like it could be a series and parallel combination, it could be cascade also. So third one is the most suitable answer, right?
Okay, series. Yes.
Okay.
Whatever we need.
Yeah.
Sir, nowadays, sir,
Hmm.
just now I read one uh, content in internet. Now, sir, parascoid cells are giving 26%
Yeah, yeah,
efficiency.
yeah. Yesterday only I.
Just now, I after 1 or 2 days before, I just write one article in internet.
Yeah, you were right. Actually, yesterday only, I guess, some days before only a report came where their NREL, this is NREL means on 3rd March, National Research Electronic Laboratory is there somewhere, where they have used the
Okay,
perovskite alkyl ammonium chloride solar cells.
parascoid.
This is containing
Yes,
alkyl,
sir.
yeah,
Parascoid, same, sir.
yeah. So it has achieved around 26.08 percentage efficiency, which is a very
Yes.
good value. So they have you can see the perovskite can be the future. The only problem with the perovskite is the stability in the ambient conditions. Only problem is this. So slowly we are
Okay.
going towards this. The advantage is this, that you can play with the band gap. You can play with the band gap. You can play with, like, you can use many types of materials. So conventional things need to be changed, because silicon is limited, right? And the process by which this silicon is made,
Sir,
and
why silicon is limited? Sir, we have the lots of land, sir.
no,
Sands.
the process by which you are making it, no, this silica that you are using, this is not
Yes, sir.
this is not environment friendly. Okay, it
Okay.
creates a
In
lot.
lab, a huge process is there, sir. Boiler 2000 degrees
Yeah,
centigrade.
exactly. So
Yes.
it emit a lot of carbon containing this pollutants in the atmosphere.
Okay, sir.
So like we are using solar for what, for decreasing pollution, for having a renewable form of
Carbon
energy.
emission.
Yeah, and then for making a solar cell, we are already doing that much pollution and harming the environment. You getting me? So this is the main reason that
Sir,
why
definitely.
we need.
Definitely.
Okay, so let's move to the last question of today, Mele. The last question is, a PN junction solar cell of area 1 centimeter square, illuminated uniformly with 100 milliwatt per centimeter square, has the following parameter. The efficiency is 15%, the VOC is zero point 0.7 volt, the FF is zero point 0.8, and the thickness is 200 micrometer. The charge of an electron is given. The average optical generation rate in centimeter cube inverse per second is. They're asking the average optical generation rate. Okay, now you have the parameters, use all of them and try to find out the formula and then the answer.
So what is the generation rate formula, sir?
That you have to figure out. I'll tell you.
This is
You have to use it, the terms, then you have to figure out the unit you see.
centimeter cube seconds. This one. Hmm. Right.
See, first of all, I'm giving you some hint. You need to calculate the fill factor, then you have to calculate the output power, and then from there you have to calculate the efficiency. Okay, now
Already given, sir,
yeah,
efficiency.
yeah, if it is given, then there is this power generation rate. Now if you will see that I have given an extra term thickness, so power generation will,
Thickness, yes.
it must be having something. So if I tell you this power generation is generally represented by G. Okay, and this G is,
Generation,
yeah,
generation rate.
yeah, generation rate, exactly. So this generation rate formula, if you remember, so you
This
have,
is alpha E something, E inverse.
yeah, that is so,
Which
in terms of this, but using all the terms that you have to make use of the short circuit current, the charge that is given, that is 1.6 into 10 to minus 19 coulomb, and the area and the thickness.
uniform efficiency 15%, 0.8. Thickness is total PN junction.
Yeah.
Sir, one thing, sir, do you have, sir, the assignment 5 total answers?
Assignment 5 total answer, if, let me check, if you can tell me this is
Yes, sir.
assignment 5. uh,
Just 4 and 5. I want to check the answer only.
just a minute. uh, if you tell me this is assignment only, if you're talking about this one, you have this one only, or this is a different one?
Yes, yes, yes. This one.
This one only. Which are the question that you want to talk?
4 and 5.
Recombination in the bottom layer of,
Sorry, 5.
only 5.
5, sir. Answer is Xn plus LP.
Hmm.
Xn greater than Ln. Okay, but here answer is wrong, I think.
uh,
Xn less than Ln.
uh,
Yes, sir. Is option D. Okay.
hmm.
But here I think some problem. I put the correct answer, but I
Okay, you didn't.
Xn less than LP and XP less than Ln.
Right, 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 you're saying it right.
So it's option C, I think, or not
Yeah,
option D.
yeah, it is option C only.
But here it's option D, sir. This is wrong.
Yeah, yeah, I think they have given it wrong.
Sir, one thing,
Did you discuss it with
sir,
Ravi?
Ravi sir also discuss. I also discuss. Sir, tell me that we will get the answer.
Yeah, yeah, okay.
We get the marks.
You will get the marks.
Marks, sir. And one thing also, sir. 1 minute, sir. Can you show me the assignments?
Okay.
1 second.
Hmm.
Not this one, sir. Yes,
Hmm.
solution.
Hmm.
Mm, sir, following six, I think. 6. No, not one. This one applied bias. Okay, another one. Sir, I told you. Which of the following methods can we quantum increase the quantum efficiency?
Hmm.
This question. Sir, can you show me the answer? Quantum efficiency by
Uh,
increase.
I don't think I have this question in this assignment.
Oh, already there, sir. I think.
This is
Sir, this one.
surface.
Question number 3.
Yeah.
Okay.
Hmm.
The question number 3, sir.
Hmm.
He also the right answer. No, sir. Sir told me that in lecture that surface passivation, light trapping, and increase in the cell width.
Increase.
Because long wave radiations will go inside. That's why.
That is right. That is right, Melee. But
But here, why two option is there?
because I think this is a right answer. Let me see. You are saying it right. For the ideal condition, increase in the cell width there, but you cannot increase the cell width beyond the limit, right?
Yes, sir. Sir, lecture already mentioned. That's why I said.
Okay. So I we have to discuss this with sir. But ideally, the answer should be C and D. But if sir has said that C, D, E should be, because you do you agree that you cannot increase the cell width beyond the limit, right? Hello.
No, 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 sir. Yes, sir. Yes, sir. Definitely we cannot. But
It's
sir, in lecture strictly mentioned. But three, increase the cell width to
yeah.
improve the photon absorb. Because I have write down
No, no, no.
the
Ideally,
major points.
ideally, the answer should be C, D, and E. I agree. This I will discuss with sir. Okay.
Okay, sir. Okay.
Okay. Okay. Now, did you?
Because yes, sir. You also right, sir. Because ideally we cannot increase the
Yeah. Ideally, you cannot
with
increase.
fixed.
Yeah, yeah. That's what I'm saying. No.
Yes. Okay, on that basis it should be okay.
But if sir has
But
mentioned it, I'll confirm it with sir.
technically, yes, sir. Technically speaking, for if you say with the long wavelength also not wasted. It will
Yeah.
be
And
on
if
the
you, I mean, if you will make it a lot thicker, no, then this like light will not be, absorbed to a much more extent deeper. You have
yes,
to be like very much you optimize it. You cannot use it very thick.
yes.
Okay. But still, I ask sir. Okay, if it is to be considered, and we will consider it.
Okay, sir.
Okay.
Okay, sir. Actually, these two should be, I think,
No,
in your question. This is
the last question, though, I agree completely. That is very straightforwardly wrong. This question I'll ask. Okay.
okay, sir.
Yeah. You give a try with question number 10, and then we can wrap up.
Because sir, till now, question assignment number five also not shown, sir.
Oh,
Answer,
okay.
not even. Sir, can you show me the formula last 10?
Okay, I'm just showing you the formula.
Okay, okay, sir. Okay,
You can calculate it. Uh, See, this is the formula. If I show you this.
okay, this is I know generation GL ISC by Q area into thickness. Okay, sir. Now I can calculate.
Yeah,
Only calculate ISC.
yeah, exactly. You just have to calculate the IFC.
ISC.
Hmm.
Okay, sir.
And put the values directly, and you will get the answer.
Yes, sir. Yes. Okay, sir. Okay, sir. Actually, sir, I told you that you are, sir. Now you are your thesis paper. I think in peroxide cells, no, sir.
Exactly,
You
exactly.
told me.
I'm
So,
working.
sir, when you actually take the class about peroxide, you
Hmm.
take a brief. I think it's beneficial for us, sir,
No, no, definitely. You don't worry. When I'll be talking about the perovskite, I'll talk in
because
detail.
it's your paper. That's why I take this, sir.
No, I can talk in detail, and I can even show you the video. The video.
Okay, sir.
Just a minute. If I will be having a. In the meantime, you solve this question. Just a minute. I'm just pausing the presentation, and I am checking if I have the video already. I can show you. Okay.
Okay.
Okay, Malay,
Yes, sir.
let me show you something. Okay, this is just a very short
Okay,
video so that
okay,
you
sir.
can be
Okay, okay,
interested. Uh, is my screen presenting?
yes,
You can see the solar cell device, right?
yes.
This is from my lab. Once some of my lab mates have done it, you have a look over it. This is the FTO glass. Okay, on this FTO
Yes.
glass we are doing this patterning. Now after this masking and patterning, we are cutting it off, we are cleaning it. Like this FTO you have to clean first of all. There are many ways. You have to clean in isopropanol, you have to clean in ozone, and then you have to like heat it also, and then you have to do selective patterning. When you are doing a selective patterning, you are following a particular pattern according to the type of architecture of the solar cell that you want to fabricate. Okay, this is the final thing. If you see, now you're cleaning it with this concentrated HCl and all this, so that no no oxygen or nothing should be there. When you're coating it, it should be clean. This is called as etching. Okay.
Etching.
Yeah.
Sir, sir, same thing is done in biomass etching.
I don't remember
Biomass
it.
sample you have to etching, na sir?
Yeah, yeah, okay. Yeah, I think so.
Um,
So now when
yes.
you have coated it and you have followed all this in the glow box, then you have to do the photovoltaic measurement in this photovoltaic device. This is a solar stimulator. If you can see, this is a solar stimulator. I am showing you.
Okay.
Now this is a dark. In this dark, you show there is nothing much. This is the IV curve that you get
Okay.
in the photovoltaic measurement. But
Okay.
but when you are taking it in presence of light, let's see we are illuminating it. You can see there is
Okay.
certain current. Fine. And when you're plotting it, you can see the value, right?
Hmm.
And they are the two lab mates who have actually demonstrated it. They are from my lab.
Okay.
So this is a general video I can show you.
Okay, sir. Okay, sir.
Okay.
Thank you, sir.
Yeah. So let me discuss the last question. The last question is like this. We know that the fill factor is this, and the efficiency formula is this. From here we can the optical generation formula is IST over Q cross area cross thickness. That means the
Hmm.
optical generation rate means the generation rate per unit area per unit thickness. Okay, so these are the given
Yes.
parameters. We just put it the values directly, and the calculation, after calculating, the answer comes as 8.37
Okay, sir.
cross.
Already it is done. 0.837.
Yeah,
Oh,
so
I
0.837.
get.
Yeah, so the answer is A. Okay.
Okay, sir. Already I have calculated. Means.
Okay, so I guess this is enough for today, Mele. And
Okay, sir. Okay, sir.
that thing of yours, I'll ask to sir. I'll confirm in the next class on Saturday.
Okay, sir.
Okay.
Okay, sir.
Okay then. See ya.
Okay, sir.
Take
Thank
care.
you.
That's all
Sir.
for today.